Asteroids detected. Collision imminent. Execute evasive maneuvers. Asteroids detected.
All systems down. Reboot failed. Reboot.
Ah, damn it. Where am I?
Daniel, is that you?
Jake? You're the first person I've seen.
I thought I was the only survivor. Where even are we, Daniel?
Well, obviously we're in Kepler 62e. But by my guess, of all this beautiful nature around us, I think we must be in the northern quadrant. From my personal guess, I would say maybe 6 or 7 quadrants over from the previous splash missions 30 years ago.
Well, I guess we should just set up camp and wait for the others.
That sounds a good idea. Let's wait here.
Guys, I finally found you! Isn't it crazy that the gravity is so heavy here?
Well, if you actually read the brief instead of slacking off, you'd know the gravity is 50% more on this planet.
Alright, buddy, I get it. It's not, those asteroids weren't my fault. They weren't on the radar. How was I supposed to know that they would come and hit us?
We picked such an idiot to be our navigator.
Guys, we need to focus. Our resources are extremely limited. And if we don't start working together now, we're never going to be able to get off this planet.
Well, I wouldn't exactly mind leaving Starth here.
Alright, buddy, I get it. Let's just focus on getting the freak out of here.
I gotta agree with Siddharth on this one. But what should we do now?
Wait, what's that?
What is that? The reports and scanner didn't cover this. It must be a real-life alien.
Wow, I never thought that the first extraterrestrial would be wearing shorts.
Wait, doesn't it look almost human?
Whatever it is, I think we should go kill it.
Guys, don't kill me, I'm human.
Really? Stay where you are. Don't get any closer.
Who are you, and how'd you get here? Guys, I'm human, look.
Wait, is this one of those antique iPhones? What are you, some kind of time traveler?
Well, I guess it's been like 30 years since this came out, so you guys weren't even born, but yeah. So are you like some sort of astronaut that crashed here and got stuck? Yeah, something like that. My mission kind of failed, so I've been surviving here, holding out hope that someone would come rescue me. Are there any others with you? Sadly, no. When we first landed, the mission was going fine. There were 5 of us. We thought we'd be off the planet in no time. Initially, we held out hope that people would come rescue us, but eventually we learned otherwise. We were scared of what would happen to us if nobody ever came. Time was running out, so we decided to send 2 people back.
Did it work, and did they come back for you?
No. Ship broke apart in the atmosphere. No chance of survival, and all critical resources were gone. Well, there's a reason I'm still surviving here.
Firstly, I'm sorry for laughing. But secondly, how do you expect us to get you off this planet? We're stuck here just like you.
Yeah, and even if the people in the command module knew that we were down here, how would they even get us out?
Guys, what do you think I've been doing for these last 30 years? I've concocted a master plan. And trust me, bro, we're getting out of this.
Well, we're still talking about things that you have. Do you have any games or things we can do?
Well, I have basketball. It doesn't really work that well because of the gravity, but I need some way to, like, pass the time, you know?
So how do you plan to get us out of here?
Well, we don't really have to get ourselves out of here. We can get them to come get us.
What do you mean by that?
Well, Kepler 62e is a planet that's rotating around the sun, right? Similar to that, your command module is still orbiting above us, but because of the interference from the atmosphere, we can only send a strong enough signal when it reaches the closest point in its orbit. the battery on your radio seems to be running low, so we can only send a signal one time.
Closest? Like closest to us?
No. Closest to Kepler 62e. That point is called the periapsis.
So we're stuck here until the command module gets to the right spot?
Exactly. And to figure that out, we need Kepler's 3 laws of planetary motion.
But say we even figure out where that point is. What happens if the signal doesn't even go through?
Well, let's just hope we don't have to get to that point.
Derek, remind us again, how can we even be sure that this orbit's an ellipse, giving us a periapsis point?
Siddharth, you're the navigator. Shouldn't you know this?
I think I lost some of my memory, Jake. I can't even remember the name of my calculus teacher.
Well, I guess I'll have to remind you how Kepler's first law of planetary motion works and how we can apply it here.
Tell me, I'm all ears.
Alright, here's how it works. We start with the mass, small m, in orbit around a much more massive object, big M. When they're a distance r apart, the total energy of the orbit is E equals 1/2 mv squared minus g big M small m over r, as shown in equation 1. Here, v is a planet's speed and g is a gravitational constant. The velocity actually has 2 perpendicular pieces, a radial part along the line of sight, which we write as r dot, and a circular part perpendicular to that, which is r times the angular velocity, or r theta dot. Since these pieces are at a right angle, we can just use the Pythagorean theorem to write the total energy in polar coordinates. E equals 1/2 m times the quantity of r dot squared plus r squared theta dot squared minus g big M small m over r, as shown in equation 2. Next, the angular momentum is L equals mr squared theta dot. If we substitute rho equals 1 over r, we can rewrite theta dot as L rho squared over m, as shown in equation 3. To find the path of the orbit, we want to see how the angle changes with rho. Using the chain rule, we can rewrite the integral for theta over time as an integral over rho. Theta equals integral of L over m times rho squared dt, which in turn equals to equation 4. Since r dot equals negative 1 over rho squared d rho over dt, this simplifies nicely. Theta is just negative integral of L over m r dot d rho, as shown in equation 5. If we rearrange our energy equation, we can isolate the squared radial velocity. R dot squared equals 2e over small m plus 2g big M rho minus L squared over small m squared rho squared, as shown in equation 6. To clean this up, we define 2 constants. R0, the semi-lattice rectum, equals L squared over g big M small m squared, equation 7, and E squared, the eccentricity, equals 1 plus 2e r0 over g big M small m, as shown in equation 8. With the little algebra, our equation for r dot becomes L over m quantity of E squared over r0 squared minus quantity of rho minus 1 over r0 squared to the power of 1/2, as shown in equation 9. Plugging this equation back into our theta integral gives us a form that integrates directly to an inverse cosine, as shown in equation 10. Rearranging that result gives us a final tracking equation for the planet, as shown in equation 11. This is a standard polar equation for an ellipse with the star sitting right at one of the focal points, and thus, according to Kepler's first law, the orbiting object must have an elliptical orbit.
Wait a sec, how'd you figure out the module's orbit? How'd you know it's about to reach the periapsis?
Wait, where is it? I don't see it.
Jake, the command module is way too far to be seen with the naked eye. And let me remind you again, the periapsis is just wherever the module is closest to the planet, not closest to us. So for all we know, it could be on the other side of the planet.
So how much time do we even have to send out the signal?
Not much. According to Kepler's second law, the module should move fastest when it's at the periapsis, so it'll pass by pretty quickly.
Wait, how does that even work though? Can you explain why that is?
Siddharth, it's simple. For the second law, as the planet moves by a tiny vector displacement dr in a time step dt, it sweeps out a small triangle. Using the angle alpha between the position vector r and dr, the area of this triangle is dA equals 1/2 r dr sine alpha, as shown in 1. We can write this more cleanly as an area vector using a cross product, dA equals 1/2 r cross dr, as shown in equation 2. Dividing by dt gives us an instantaneous rate of area swept out, a dot, which is 1/2 r cross r dot,
as shown in equation 3. To see if this rate changes over time, we take the time derivative again to find the acceleration of the area. A double dot equals 1/2 times the quantity of r dot cross r dot plus r cross r double dot, as shown in equation 4. The first term drops out immediately because any vector crossed with itself is 0. Thus, r dot cross r dot equals 0, as shown in equation 5. The second term contains r double dot, which is the planet's acceleration vector. Since gravity is a central force pulling directly towards the star, this acceleration is completely parallel to the position vector r, meaning their cross product r cross r double dot is also 0, as shown in equation 6. Because the entire derivative is 0, a double dot equals 0, meaning the rate of sweeping out area is completely constant, as shown in equation 7.
That means quick, guys. Let's get to the high ground and set up the beacon. There's no more time to waste.
Well, guys, we have to be accurate. If we miss this chance, it'll be another few months before the command module reaches the periapsis again. Our resources are extremely limited, and we don't have time to waste.
Guys, come on. I can't even survive another week with Jake.
Here comes the hard part. We gotta use Kepler's second law to calculate the speed of orbit at that point.
What are you talking about? I thought objects orbited at constant speed.
Guys, how do you even get here without knowing this? Remember back to Kepler's second law. A line connecting a planet to an object that's orbiting it will always sweep equal areas over equal amounts of time. So that basically means that over 2 equal periods of time, the area of the orbital arc will be the same always.
Why do the planets even change orbiting speeds then? How's that even related?
Orbital speeds change because they orbit in ellipses. So for Kepler's second law to be true, the velocity has to change.
Wow, that's pretty interesting. Now let's figure out when to send this signal.
That's where Kepler's third law comes in. Orbiting period is directly proportional to the radius of the orbit. I remember the proof from high school.
For Kepler's third law, we want to show that the square of the orbital period is proportional to the cube of the orbit size. The total period, capital T, is the total area of the ellipse divided by the constant rate at which area is swept out. The total area of an ellipse is pi times a times b. Since b equals a times the square root of 1 minus e squared, the total area becomes pi times a squared times the square root of 1 minus e squared. From earlier, our constant sweeping rate is L over 2m. So when we divide the total area by that rate, we get the orbital period. T equals m over L times 2 pi a squared times the square root of 1 minus e squared. Now we square both sides. That gives us t squared equals m squared over L squared times 4 pi squared a to the 4th times 1 minus e squared. Next, we use the geometry of an ellipse. By setting up a right triangle with the focus and the center, the Pythagorean theorem gives us 2a minus r naught all squared equals 4a squared e squared plus r naught squared. This simplifies to r naught equals a times 1 minus e squared. Now we substitute our physical definition of r naught from the first law into this geometric equation. That gives us m squared over L squared equals 1 over gma times 1 minus e squared. Finally, we plug this into our squared period equation. The 1 minus e squared terms cancel out perfectly, leaving us with t squared equals 4 pi squared over gm times a cubed. This proves Kepler's third law. The square of the orbital period is directly proportional to the cube of the orbital size.
We can use this to find the orbital period of the command module. When we were on the spacecraft, I remember that the closest point C to Kepler 62e was 18,000 kilometers, and the furthest point A was 78,000 kilometers, and the period of orbit for our spacecraft was 8 hours. After we launched the command module from our spacecraft, we immediately encountered those asteroids. But right before we ejected, I remember glancing at the control panel and seeing that we're approaching the planet at 4,000 kilometers per hour, and our orbital period was shrinking by 30 minutes per hour. First, we can find A1, or the original semi-major axis of the spacecraft. The semi-major axis is an object's average distance from what it's orbiting, and is half of the longest diameter of the ellipse. For the spacecraft, A1 is c plus a all over 2, which is 48,000 kilometers. Then, using Kepler's third law, orbital period squared is proportional to semi-major axis cubed, we can create this formula. T squared is equal to a cubed times constant k. Isolating k and substituting values for t1 and a1 results in k being equal to 64 over 48,000 cubed. Now, going back to our command module, we can use related rates and differentiate Kepler's third law with respect to time. 2 times t2 times the derivative of t2 with respect to time is equal to 3 times k times a2 squared times the derivative of a2 with respect to time. Since the control panel showed that dt2 over dt is negative 0.5, dA2 over dt is negative 4,000, and k is 64 over 48,000 cubed, we can plug in values into this equation. After isolating t2, it's equal to 6.944 times 10 to the negative 9 times a2. Because Kepler's third law applied to the command module has t2 squared isolated on one side, we can square the equation that we found. Then, substituting 64 over 48,000 cubed times a2 cubed for t2 squared, we can get the equation 6.944 times 10 to the negative 9th times a2 squared whole squared is equal to 64 over 48,000 cubed times a2 cubed. After simplifying, a2 is equal to 5.787 times 10 to the negative 13 over 4.8225 times 10 to the negative 17. This is equal to 12,000. Thus, the semi-major axis of the command module is 12,000 kilometers. Finally, using Kepler's third law ratios, t2 over t1 whole squared is equal to a2 over a1 whole cubed. Thus, t2 over 8 whole squared is equal to 12,000 over 48,000 whole cubed. So t2 squared over 64 equals 1 over 64, and t2 is 1 hour. So the period of the command module is only 1 hour. We only have 45 minutes left.
Well done, Fedor.
We should try to get to that mountain on the map to get the best chance of clear signal.
Good idea.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
So, did it work? I don't know. I guess we'll have to wait and see if anything happens.
Alright guys, we should just set up camp here. We don't know how long this is gonna take, so we're gonna have to settle in for the long haul and see where this goes.
Yo, wake up, what are you doing?
Shit, I must have fallen asleep.
You know what happened? The boss finds out, right?
The boss will not find out. He's still grieving about his dreaded failed mission.
Alright, just be careful.
Alright.